our next theorem is, if the modulus of a certain sequence, the limit of the modulus of a certain sequence is equal to 0, then the limit of the same sequence without the modulus is also equal to 0. We'll do an example that goes with this theorem. So if we consider the sequence -1 to the power n divided by n. Now see, this is also a oscillating sequence. I'll explain that part a bit later, but anyway, now you can clearly see that if we take if we observe the values of this sequence, then a1 will be -1 to the power 1 over 1, which is equal to -1, and a2 will be equal to -1 2 over 2, and that is equal to positive half, and a3 will be equal to -1 3 over 3, and that is equal to -1 over 3. So our sequence will be like this. Our sequence will be it will start from -1 half, -1 over 3, -1 over 4. Likewise, no, this should be positive and this will be negative. So see here, it's like 1 divided by 2, 1 divided by 3, 1 divided by 4, 1 divided by 5, but you have a negative term one after the other, right? So if we just plot this one, you can see at each and every point, if we start from 1, you have -1, and at 2 you have half, and then at 3 you have -1 over 3, at 4 you have this one. See, likewise it will, although it oscillates in between negative and positive, it will eventually reach a certain value, right? See, it oscillates, but not as it was in the previous case. In the previous case, remember, we had -1 to the power n. So the distance between these points were the same in this case. But here in this example, or in this sequence, we have a sequence that oscillates between negatives and positives. But the thing is, the distance will be slowly reduced, and then eventually it will reach a certain value, which is the limit point. But in order to use the given theorem, we don't need any of these data. What we have to do is, we just have to consider the modulus of the given sequence. Now in this case, the given sequence is an, and then if we consider the modulus, then it becomes the modulus of this term. So when we are taking the modulus, we can distribute it to the numerator and the denominator separately, and since n is a positive term, you can write it like this. And here you can see, by changing n, this numerator will take values it will only take values out of 1 and -1, right? So when n is odd, this becomes -1, and when n is even, this becomes +1. So when you take the modulus, then it will always be equal to +1. In other words, if we have the sequence like this, then the modulus of that sequence will be equal to 1 over n, right? Then we can simply consider the limit of that sequence. So that means we just consider the limit of this 1 over n sequence, right? And that is equal to 0. When n takes a large number, this becomes 0, right? So that means we have proved that the modulus of this sequence is equal to 0. So from the theorem you can say that the normal sequence without considering the modulus should also go to 0. That comes from the theorem. Okay, so like the picture I described is something else, right? Now by looking at the picture also without any of these theorems, you can say that the sequence looks like that it approaches 0 eventually, but we really don't need this picture to prove the convergence of this given sequence. We can directly use the above theorem to prove the convergence of this theorem, right? And I should say one more thing about this if then statements. Okay, now here in this theorem it says if the modulus of the sequence is equal to 0, then we have this one, but it does not say anything about the other direction. Now these if then statements are very, like, you have to understand these if then statements very carefully. Okay, now I don't have time to explain all the logic behind these statements. Okay, but now at least for the time being you have to carefully understand that if this statement is valid only on this direction, if we have this one, we know this result. That's all we know from this given statement. Okay, we cannot conclude anything, like if we have this one, we cannot conclude anything about the term in the left hand side to the then statement, like this. Like now here we can consider this if then statement as this part and this part, right? I will call this part as the right hand side and I will call this part as the left hand side. So this if then statement is something, some information where the left hand side is true. When the left hand side is true, then the right hand side should be true. But if the right hand side is true, we cannot predict anything about the left hand side. Like we don't have enough information to predict anything about the right hand side. Okay, so whenever you have a if then statement, you should be careful. If then statement is only valid in this direction, right? So if we have the left hand side, then we know the right hand side. Okay, and not the other way. And in the next example, in the next video also, we will do another example.